Okay. All right. Ladies and gentlemen, dear colleagues and friends, and in particular, Ifan's family, welcome to Ifan's inaugural lecture. So, my name is Sandrine Heutz. I'm the head of the Department of Materials, and it's my great pleasure to welcome you. And firstly, it falls to me to ensure that you're all safe and to note the exits at the front there and here at the back. Yeah, this lecture theatre is really packed, and I think the lecture was oversubscribed. So, we have to make sure that we can all feel safe here and exit in the right way. So it's a particular pleasure for the Materials Department to celebrate Ifan's accession to the professorship, as he was an undergraduate in materials in 1997 to 2001, before moving on to Cambridge for his PhD, then MIT and Denmark. We were delighted to have him back in 2017, and he immediately made his mark in many ways, building a vibrant and diverse research group and founding the electrochemistry network. But I'm sure we're going to hear lots about this. I should say one of Ifan's roles in the department that is kind of useful to all of us and in the community here is as a project coordinator with responsibility of allocating over 120, and that's a very understatement, final year undergraduate and MSc projects to his academic colleagues, which means he's incredibly popular. Or rather, the fact that this room is still so full of his friends, despite him assigning such a heavy workload, is really a testament to the great way that he does his job, his fairness and consideration in everything he does. But I won't go over too many biographical details, as he's promising to do this, to give us an overview of his personal and scientific journey over the last 2 decades. Ifan's talk is Chasing Volcanoes, Catalyzing Our Way to a More Sustainable Future. If, like me, you thought that this is a clever and intriguing title and did a bit of Googling on catalyzing volcanoes, you will find Ifan in 2 of the 3 top entries, illustrating a catalysis principle linked to a 1912 Nobel Prize, such as Ifan's impact and established international renown that he is linked to such distinguished discoveries. I'm also reassured that there will be no health and safety concerns that there might be if we were more in an earth science type setting here. Ifan, congratulations on your success. Thank you for being a star in our department who is shining ever more brightly, and we're looking forward to hearing your story. Thank you.
So thank you for the very kind introduction. So it really means a lot to me to have so many friends here today and so many a family, as well as colleagues, former students, current students, and so forth. I think it's rare to have an occasion where you can unite everyone together. So it really means a lot that you're all here. So I'm going to start with some basics and define what is a catalyst. So according to the definition I found, it's a substance that increases the rate of a chemical reaction without getting consumed. So interestingly enough, the origin is the early 20th century. But today, catalysis forms a cornerstone of our modern society. It produces fertilizers we use for agriculture, produces polymers or plastics, fuels, and catalytic converters in automotive vehicles. So to give a more specific example, one really important catalytic process is the Haber-Bosch process, which a lot of you might have heard about at school. So you basically react nitrogen and hydrogen to make ammonia. So 2 examples of a catalyst that actually can carry out this reaction. One is the nitrogenase enzyme in the roots of plants. So it happens just under ambient conditions, so room temperature, atmospheric pressure. Well, the Haber-Bosch process occurs in these really big plants. The reason that occurs in these big plants is because you need very high temperatures and pressures. Means you need economies of scale to get it to work. And this is an example of the nanoparticle catalyst. I believe this is ruthenium that they use to carry out the reaction. So it turns out that Nature, at the end of the 20th century, they had an essay on the importance of the scientific discoveries of the 20th century, and said, actually, the most important invention of the 20th century was the discovery of the Haber-Bosch process. So more important than penicillin, more important than the transistor, and more important than many other things. I'll explain why in a minute. So typically what you're doing with a catalyst is you take a reactant, so in case of Haber-Bosch, you take nitrogen and hydrogen, and you react it until you get the final product, ammonia. So you have a catalytic cycle. So here's electrochemical nitrogen reduction. You have nitrogen, it absorbs, then it gets hydrogenated. So the nitrogen atoms, there's two blue atoms, and the hydrogen is a little white atom. So you sequentially add more and more hydrogen. You first make one molecule of ammonia, then you add more hydrogen again, and then you make a second molecule of ammonia, and you start with a clean surface, and nitrogen goes on it again. So essentially what the catalyst does is you can think about it as trying to climb over a mountain. So this is the start point where you have nitrogen, this is the final point where you have ammonia. And a good catalyst will build a tunnel all the way through to minimize the amount of energy you need. So if you look at something like gold, so nitrogen is very, very inert, and gold is very, very inert as well. So it's a noble metal, it doesn't want to react. So it's really, really uphill to get nitrogen to react with gold. So it's like trying to climb up all the way these huge peaks, and you probably won't actually get to the other side if you use gold as a catalyst. Conversely, if you look at something like rhenium, another metal is a lot more reactive, then it's not so difficult to get nitrogen on in the first place. But then what tends to happen is you tend to get poisoned by some of these species containing nitrogen further down in the reaction. So the ideal catalyst will have a completely flat path from the start to the finish. So it'd be like a tunnel going just straight across here. So I'm not going to make the talk too dry, so I'm going to try and, I realize a lot of you are not scientists, so I'm going to try and intersperse some of the science with some personal stories as well. So I think that as physical scientists, we often try and make a model for trying to try and understand the phenomenon and apply it to other phenomena. So I guess the question is whether we could actually apply this kind of catalytic cycle towards my career. So people have asked me if I've actually gone in a full cycle. So I started, as Sandrine mentioned, started as an undergraduate, then I worked in consultancy, and then I was a PhD student, and then I did a lot of other things, and eventually went back to Imperial College. So I think I can say I haven't been consumed in this process. So this is probably not a very apt analogy. So the other thing you could say, just that everything's going better and better and better all the time. But actually, I have to say, it's not the case. So actually, more likely is actually, so I'm probably more satisfied now than I ever have been in my career, but there's been a lot of ups and downs on the way as well. And I think it's important, especially for the young scientists here, to kind of explain what some of those ups and downs are. So now I'll go back to give a general motivation why catalysis is important. So I'll go back to the Haber-Bosch process. Like I said, it was invented in 1913 for making ammonia. The reason it's important is ammonia is converted to make nitrates of our body mass is nitrogen. So 1.6% of our body mass is actually from Haber-Bosch processes. This is really, 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 really important. I can't think of anything else which has as much influence on our lives. So, and actually, if you look at this graph here, this is an estimate of what Haber-Bosch has had on humanity, on the world population. So this is our current, a few years ago, world population. And this is what the estimate is, our world population would have been without Haber-Bosch. Essentially, because before the Second World War, there were constant famines happening. And the only way we got around it was actually using fertilizers. But still many parts of the world, for example, sub-Saharan Africa, still lack fertilizers. And the main reason for that is that ammonia nitrates fertilizers not particularly easy to transport or store. So you might recall the accident in Lebanon a few years ago of a nitrate fertilizers explosion. And in sub-Saharan Africa, because they lack transportation infrastructure, they often suffer from famine in those parts of the world without fertilizers. This is a big problem. And maybe the other big problem is Haber-Bosch is not sustainable at all. So hydrogen comes from natural gas, methane. So it's about 1% to 2% of global emissions, which is equivalent to the global aviation industry. So if we want to go to net zero by 2050, we need to get rid of this or completely decarbonize fertilizer production. So, I've given this specific example for ammonia production. So as I mentioned, ammonia is used for making fertilizers. So I find this diagram quite useful. It's a Sankey diagram showing the energy inputs and energy outputs in the global chemical industry. So you can see the kind of products we make, apart from fertilizers, thermoplastics, solvents, and so forth. And typical building blocks, apart from ammonia, also ethylene, methanol, to a lesser extent also hydrogen peroxide, but all the energy input right now comes from fossil fuels. So we need to completely get rid of these fossil fuels as a source of power for the chemical industry. So the really positive story over the past few years has actually been the rise of renewable energy, or more specifically, if you look at the mean cost of electricity, it's dropped really, really dramatically. Sorry, electricity from renewables, more specifically. If you went back further, you'd see that it dropped many orders of magnitude, especially from solar. So now, if you look at the mean cost of electricity, it's actually cheaper than the fossil fuel equivalent if you get it from renewables. And because of this increased, the decreased cost of renewables, if you looked at last year, actually, there's a big jump in the amount of renewable electricity stored. Still not happening fast enough, but it is happening. So could we use electricity to power the chemical industry? So the answer is, well, to my mind, yes. We could use electrochemistry. So as you might have noticed from my title slide, I'm a professor in electrochemistry. So electrochemistry is a branch of chemistry that deals with the relations between electrical and chemical phenomena. So whether you know it or not, we're all familiar with electrochemistry. So all of us carry a smartphone. Also, they have lithium-ion batteries in them. And also, we now start to see lots of automotive vehicles being sold in the UK made from lithium-ion batteries. Also, large-scale processes already using electrochemistry industry, including the production of chlorine and the production of aluminium. So for those chemicals I mentioned previously, like ammonia, ethylene, and methanol, hydrogen peroxide, it turns out we've been able to make them using electrochemistry, so using electricity. So in principle, we could actually eventually use renewable electricity to make these really important chemical building blocks. So, I've been able to make them, as I mentioned, in my lab, not always just in the lab. Also, we've started a spin-out company making hydrogen peroxide electrochemically as well. So it turns out for a lot of the processes I'm looking at, they occur at quite low temperatures. You need a good catalyst at the electrodes. And the electrocatalyst is what you call the catalyst in an electrochemical device. So that's what I and my group investigate. So to appreciate what a catalyst is, I've got a cross-section here of a water electrolyzer. So essentially what you've got, so what you could, an electrolyzer could be a means of making hydrogen. So essentially what you do is you split water into hydrogen and oxygen using electricity, ideally from renewables. So you have in the middle a membrane that only conducts protons, and at the side you have the electrochemical reactions. You have hydrogen being evolved on one side and oxygen being evolved at the other side. So electrocatalyst is actually these little nanoparticles here. So you have iridium oxide nanoparticles at the anode electrode, and you have platinum dispersed on carbon at the cathode. So ideal way of actually testing different electrocatalysts would be to take actual device and put it together. But you can imagine doing it is not that easy because there's a lot of different steps to put it together. So it becomes, it's difficult to actually then see what's the fundamental effect of changing the material. And even if you look at these materials, you can see like this platinum nanoparticles, these black dots, have a lot of different sizes and shape, and each different size will have a different reactivity. So often what we do is try to look at more model systems and the more model conditions, where we're just changing parameters more carefully. So for example, we often look at size-selected nanoparticles. So these are typical size nanoparticles, that's 5 nanometers across. Or we could look at oriented thin films, or even look at single crystals, that's 5 millimeters across. So it's quite interesting if you just consider the length scale completely different from this. There's about a million times difference between the size of these particles and this single crystal here. So whereas in an actual device, you often use a polymeric solid electrolyte, often what we use instead is liquid electrolyte instead, and we rotate it to stir the solution and bring reactive gases to and from the electrodes we're studying. So, so using this, we can get and study the role of a catalyst under very well-defined conditions. And, and often what we do is I collaborate a lot with, I keep on touching the wrong keyboard. So I collaborate with a lot of people doing theoretical chemists, synthetic chemists, and people doing characterization. Ideally, what we'd like to do is discover new materials in a seamless loop. We're not always, the loop usually gets broken at some point up to now, but ideally we would be working in a closed loop following this schematic. So I'll give you a few examples of that now. So I guess first I'll start off with what drew me to electrochemistry. So as I mentioned, well, as Sandrine already mentioned, and I mentioned as well, I was an undergraduate at the Department of Materials here at Imperial College. So here I am, actually, in the middle here. This is in 2001. And actually, it's really funny, actually, being back here, because it's a bit like when you see a film with a different, remade in the same spot with different actors, because pretty much everyone has changed. So Mary, who'll give the vote of thanks later, has just arrived. She's the cool new lecturer. And actually, I think the only full-time member of staff was Darukshan, who's from the whole department at the time, if I'm not mistaken. Apologies if I have omitted someone. So for me, moving here to be at Imperial College was really, really a big thing. It was very, very exciting. So actually, it's funny, actually, looking back at that period, we didn't really have so many social media or smartphones. So I didn't have actually any photos of being a student. I had photos of me graduating, but not working in the lab or anything like that. So, but I really, really enjoyed being here at the department and also living in London. So it was very, very exciting, and it was very cosmopolitan, and also it was very scientifically stimulating. So I was very lucky we had as John Kilner, who's now a Professor Emeritus in the department. He was our lecturer for electroceramics. And he was the one who really brought me into electrochemistry. It just shows how important a good teacher is, indeed. So essentially, he's a keen advocate for hydrogen fuel cells. So you might remember, so actually, people are asking me, are there going to be any explosions? I hate explosions. So I have an aversion to explosions, so I'm afraid I'll only have to show you an explosion by video. But this is a balloon filled with hydrogen and oxygen. If you detonate it, explodes, and releases a lot of energy. So that's reaction hydrogen and oxygen, you make water. So a fuel cell, actually, what it does is harnesses the energy in a much more controlled way. So essentially, you don't have hydrogen and oxygen next to each other. You get them separated by a membrane. The membrane conducts ions of oxygen through it. And so the kind of fuel cells that John Kilner is keen on is a solid oxide fuel cells that work at high temperatures. So it's like a battery, essentially, but you feed it fuel. And typically, what you'll do is you put a lot of these fuel cells in series, and you make a stack. And then you can power a home with this fuel cell. And this kind of fuel cell usually works very efficiently. So I was very excited after my favorite lecturer actually allowed me to be, well, I'm not sure if it's him who allowed it, he was probably the master's project coordinator at the time, but allowed me to actually do my master's project with him. And so we were actually looking at the materials you use for this membrane. So we're looking at oxides, so a mixture of metal and oxygen that were doped. So we're looking at cerium-doped oxides. And usually when you put a dopant, you make a vacancy, so like a hole in the structure. When you heat it up, you'll find the oxygen ions actually go through this. And this is really important in order to allow this fuel cell to work. So usually they work at several hundred degrees Celsius. There's a lot of people who are interested in trying to get the temperature to go lower for many practical reasons. So what you want is to get the oxygen to move as easily as possible. So essentially what I did was that I studied how the activation energy for oxygen transport, so essentially changed as a function of amount of neodymium, so the second metal you put in this oxide. So the activation energy is essentially telling you how big is the energy barrier for the oxygen to jump around. So the higher the value, the more difficult it is. And what we found is actually that the activation energy was lower than what people had reported for any other materials. And it was slightly counterintuitive, because previously, because neodymium it has a slight size mismatch with cerium oxide, and people usually thought you need to minimize the size mismatch. So this is exciting for me. So in principle, if you could optimize it further, you could even use it eventually in a fuel cell. It hasn't happened, but there was hope at the time. So I really, really relished those meetings I had with John Kilner back then. And it was really inspirational experience for me. And actually, I even got, a few years later, actually published this paper as first author. And what really I liked about it was the electrochemistry, or ionics, as John would call it. It leverages atomic scale insight to solve problems that are really important for humanity. And I also found scientific research exciting and rewarding. I learned from this as well. This is important for what comes next. So despite that, actually, I thought, I want to stay in London. And I thought, I don't want to just, and if I'm going to stay in London, I probably want to stay at Imperial College, but I don't want, I thought that was a bit limiting, so I'm not ready to go back to Imperial College yet. So I wanted to do something different. So I decided, why not work as an engineering consultant? So I went to work in Biro Happold Consulting Engineers. So this is me actually, again, like I mentioned, I didn't have any photos of me being professional, but this is a photo of me on holiday in LA. So it was just, it's quite convenient. It was just north of Oxford Street. And the thing was, so I thought, okay, I'm a material scientist. People use a lot of different materials for facades. I was in the facades department for facades of buildings. And I actually have a lot of really useful insights. I was really wrong, actually. So all I had to do in the end was just count cracks on all these famous buildings around London. And I'd have builders shouting at me saying, "You don't know anything. Who are you?" And I'd be like, "I just study ceramics and glasses." I remember looking at Cumberland Hotel and Marble Arch with binoculars through December. It felt like a spy. But so I learned a lot from this experience. I realized it really wasn't for me. So I think construction industry is really conservative in use of new materials because you want the material to last for a long time. And I have no aptitude for thinking in 3D. So I remember I had to count all the surface area types on the Brunswick building. It was horrible. Like, I just think in 2D, or even in 1D. So I'm more interested in molecular scale phenomena than macroscopic phenomena. And I kept on getting told that was too academic as well. So really, there was no option for me to go back to academia. So I went to actually do a PhD at Cambridge University. The supervisor, Derek Frey. So what I looked at was catalysts. This is the first time I actually started working with catalysts for redox flow batteries. So redox flow batteries is essentially a way of, they're like a regular battery, except that you charge up a solution and you store it in a separate tank. And then the reason you store it in a separate tank is usually in a regular battery, the amount of energy you can store is controlled by the dimensions of the cell. But if you store it in a separate tank, you decouple the two. So this would be really useful for large-scale energy storage. So the premise of my PhD was that these special tungsten and sulfide materials would be really good as catalysts. So my PhD years were a lot of fun. So I had a lot of nice dinners, and we did typical Cambridge things, which I would probably not do now, but I still did then. But like go to Mayball, and this is me. This is the only photo I had in my lab of my late uncle Anthony. And despite that, something was amiss. If you look here, actually, this is the only paper I published for my PhD, and I published it 10 years after I started my PhD, which is not good at all. And it was actually really quite a terrible experience for me. So the problem was actually the company that was sponsoring me. They got closed down 2 months after I started, and I thought, okay, this is going to be great. I have even more freedom. But actually, I was the only aqueous electrochemist, the only electrochemist working with water, and everyone else was working above 500 degrees. I was working at room temperature. So I really had to learn everything myself. So the basic premise of the PhD was actually that these particles would be really good at oxidizing and reducing sulfides in solution. So typically, tungsten sulfide has a layered structure. This is how the atoms look. And you usually have these little platelets. You have edge planes here, and then you have the basal planes. It's the flat planes here. So what you do in these fullerene-like structures, like balls, you essentially remove these edge planes. They're all curved over. So we thought there was a lot of hype about nanomaterials at the time, about 20 years ago, and a lot of people thought, if it's nano, it's good. So then, actually, I tested the material. So essentially what this is, so here we've got what's called a Tafel plot. So it's a potential. I should say, it's a current density. So this is a reaction rate. So you want this to be as high as possible. The potential is how much a push you give to the reaction. So ideally, you want as high currents as possible, as close as possible to the theoretical value, which is here on either side. So this is when you're going driving the battery one way. This is when you're driving the other way. And what we found is actually this really novel nanomaterial is actually terrible for the reaction. And so even regular not nanomaterial was actually better. And I was running out of time in my PhD, and I thought, how can I actually make it better and make the? So actually, it's brute force. So I just took the tungsten sulfide particles and put them in what's called a ball mill, and you shake it around and batter it to pieces, and then you ended up having a lot more defects. So I think if I'd really read my literature properly, I thought I read well, I'd learned that actually the catalytic reactor phase is actually the edges. And by removing the edges, you make these particles really, really useless. So that was a bad experience for me, actually. So I didn't finish my PhD until 2010. I did graduate eventually. And it was a proud day for my family, but a slightly painful day for me. But I did learn a lot from my PhD. So what did I learn? So everything I learned was the hard way, with almost nothing to show for it at the end of my PhD. So I had no papers except for my master's. And I realized material synthesis is really, really difficult. So I'd leave that to other colleagues like Magda. Despite the hype, nanostructured materials are often better than other materials, but in this case, they were terrible. So really, I think what was quite important when you think about tailoring the functionality of materials, you should first establish what characteristics are needed, rather than thinking that looking at materials that are interesting to synthesize or what looks nice in the microscope as well. So I found PhD a lot more difficult than masters, but I did find my calling. I thought that was electrocatalysis. I thought it would be good to do research in a group whose goals are more aligned with my own. So then I actually went to Denmark just in January 2008 without a PhD, starting a postdoc. Nobody could ask me about that. So every time someone asked me about a PhD, I changed the topic and I got really scared, even with my family. So it was a really, really difficult experience because it was difficult to people say, oh, you must have papers. I said, no, I don't have any papers except for my master's. So it was really, really hard, actually. But actually, so then so I was a postdoc until December 2010. So remember the first 2 years I didn't even have a PhD. And then actually I became assistant professor. It was really, I kind of became assistant professor through the back door, because they essentially were, a senior professor had left, and they said, do you want to be professor? I said, sure. I didn't even have an interview. So after the hell I had from my PhD, I actually was very, very fortunate in that way, and I was quite privileged. So my director of our center was Iep Kirkendorf. The first thing he said, we're here to do good science. I thought this is actually something that fits in well with me. So in the group, what they tended to do was work with more conventional, traditional heterogeneous catalysis, like the Haber-Bosch catalyst that I mentioned at the beginning of the talk. And we barely had an electrochemistry lab, actually. So it actually wasn't a lab at all. We were in an office full of theorists, and so electrochemists usually work with wet chemistry, so you usually expect to have a sink. We didn't even have a sink in the lab. It was in an old office. But it was really good, actually. I worked a lot really closely with theorists, and actually probably the leading theorists in my field. So aside from the science, I also had a lot of fun. This is actually the lab. This is interesting. We traveled a bit to different places and showed my parents around Copenhagen. And it was nice, even though the first 2 years I completely stayed at home all the time. I didn't make new friends. I just hoped to be working on my thesis when I didn't actually do anything. So anyway, so the thing we were trying to work on, or we were working on, was looking at polymer electrolyte membrane fuel cells. So they're also for getting power out of hydrogen, similar to ones I showed before, except they work at much lower temperatures. So typically, you feed hydrogen into the cell, you feed oxygen, you make water, and then you stack the cells together, and then you put them into a car. So there's, or you could put them even into a truck. So I know lithium-ion battery cars are now all the rage, but actually I think there's still potential for fuel cell cars, and they're particularly useful for trucks and also for trains and even for airplanes. So so Toyota as a company is really at the forefront of fuel cell. I visited them twice. So the first time I visited them, actually, they offered me the chance to drive their fuel cell car. I had to decline because I haven't driven for 15 years. I don't think I would have been invited to the second time if I had actually driven it. So the good thing, so you're powered by hydrogen. Hydrogen is really, really light. And you can just refuel a fuel cell instantly. So it compares a lot more favorably relative to batteries in that respect. But there's a catch. You need a lot of platinum catalysts at the electrode. So why would we bother using platinum? It seems like stupid, really. Well, partially, it's because you're working with a very acidic electrolyte. It means every metal dissolves except for platinum and gold. And also because you need high catalytic activity or reaction rates. So luckily, in the group where I was, they were doing a lot of theoretical calculations to try and understand electrochemical systems. And electrochemistry, usually what we do is we measure current as a function of potential, and we try and conjecture what's going on. And it's very rough because it's very difficult to understand this complicated surface. So actually, what they do, so my former colleagues Jens Nurskov and Jan Rosmeister, they'd had a lot of experience looking at more simple systems based on the gas phase catalysis. And they translated a lot of that knowledge to electrochemical systems, where you have a solvent in a way it's a bit more complex. So essentially, for an oxygen reduction in a fuel cell, you want to go from oxygen to water as easily as possible. So essentially, so you have an oxygen molecule, then you protonate it, you add a hydrogen there. So these two are oxygen atoms. Protonate further, you make one more oxygen molecule, water molecule, and then protonate further, make hydroxyl, and then you make water. So this is the overall pathway. So ideally, you want to react with all these different species, but you don't want to react too strongly with them, otherwise you'll never go the complete cycle. So you need to bind an intermediate amount to it. The problem is that all of them bind via the oxygen atom, so they all bind in a very similar way. So this actually means, it constrains the reaction somewhat. So the problem is actually the binding energies of how strongly all these different species are bound actually correlated to each other. So this constrains the reaction and constrains the efficiency of fuel cells. But the good thing is if you know the binding of one of these different reactive intermediates, you know the binding of the other intermediates. So then you get what's called a volcano plot. So this is what from the title for my talk. So essentially, in catalysis, what we say is the optimum catalyst should bind moderately to the reaction intermediate. So in this case, if you look at something like gold, gold will be really, really difficult to react with oxygen. Gold is a noble metal. If you look at, and you'll be limited by reaction with oxygen. Or if you look at a very reactive surface like molybdenum or iron, so you know iron reacts readily with oxygen to make rust, you'll also get poisoned by the reaction with oxygen. So platinum is actually ideal because it has a moderate binding to reaction intermediates. You could get even higher if you just weaken the binding to oxygen a little bit further. So this is what the volcano plot. So this actually, as Sandrine mentioned at the beginning, is actually an old principle from the Nobel Prize winner, Paul Sabatier, from over a century ago, who indeed said that almost optimal catalysts exhibit moderate binding to reaction intermediates. So it turns out, actually, the first time this Sabatier principle was applied in electrocatalysis was actually by Imperial College alumni, Roger Parsons. But he had a purely, at the time, he didn't have any data to populate it, but it was more a supposition. So now, today, actually, volcanoes are everywhere in electrocatalysis or catalysis at large, even on oxides here for oxygen production. Previously, I was showing metals, and also for the Haber-Bosch process. You know, the ruthenium works best because of moderate binding to nitrogen. So usually when you look at these volcanoes, actually, what typically people do is they either have theoretical activity, and the theoretical activity is a function of a theoretical binding to reaction intermediates, or they have more indirect experimental descriptor on the x-axis. So one of the nice things what we had in DTU was the ability to work with single crystals. So essentially what you can do is you can take a macroscopic crystal. It's all been oriented to expose almost entirely one crystal facet. So this is a closely packed plane of platinum. So you can see all the balls closely packed together. And I was working with Alexander Bandarenko, a really good team in the lab, in our very rudimentary lab, actually. And what we found is actually, we found some theoretical studies saying if you just put a little bit of copper in the very surface layer, you should be able to weaken the binding of platinum to reactive intermediates. And we thought if we could just change the amount of copper, we could actually try and map out the volcano. And this is what we did. Actually, this is the theoretical prediction. This is actually the experimental prediction. And we didn't quite reach the maximum predicted by theory, but this is to be expected. So this is as good as we could possibly hope for agreement between experiments and theory. So this is really exciting for us to work on. So we later tried to actually look for other new alloys, because the problem with actually this alloy, you're relying on just a tiny amount of copper. That copper will leach away in the acidic environment of a fuel cell. So bulk alloys, where you have the same composition throughout the middle, would be more appropriate. So typically what we were looking at alloys of platinum and rare earth metals, lanthanides more specifically. And typically what we found was that it formed a very compressed platinum structure at the surface. And the nice thing with the lanthanides is they have quite a boring chemistry, all the same. The only thing you're changing is actually the size of the atom. So we suppose, well, we think that the activity is controlled by the platinum-platinum distance at the surface. So that means we should be able to actually reach optimal activity by just changing the lanthanides. And this is exactly what we did. We've got another volcano here, actually, and we've got extremely high activity. So a good thing about this, if you put this in principle in a fuel cell, you could get away with using about 5 times less platinum. So you could actually use scale-up fuel cells more easily. So apart from actually looking at oxygen reduction to water, which is the key reaction in fuel cells, we also thought, what else can we use this reaction for? So in fuel cells, you should make water. There's another product you can make, which is hydrogen peroxide. There you maintain the oxygen-oxygen bond, and then you don't split it apart. So some of you might be familiar with hydrogen peroxide as a bleaching agent. And it turns out it's actually very environmentally friendly. It's not toxic like chlorine, and its use is going up a lot. And it's used especially for bleaching paper, also for cleaning wastewater, and also for chemical synthesis. So right now it's produced in centralized locations. Centralized locations are very high concentrations. There's about 55 plants in the world. So then you make it high concentration, then you have to transport it to the point of consumption. So this is not without its dangers. There's been 2 very well documented accidents, including an M25 motorway, where people had a big canister of hydrogen peroxide, it broke apart and exploded. So usually, if you're trying to clean water of hydrogen peroxide, you only need a really, really low amount of it, around 0.1%. So we started talking to people in industry and said it'd be great if you could actually use electrochemistry for making hydrogen peroxide. We said, well, actually you can. We didn't really understand why people were not trying to do it. So essentially what you can do is all you need is hydrogen all you need is water and oxygen and electricity, and then you can get dilute peroxide in pure water. What's really important is that you keep intact this oxygen-oxygen bond and don't make the more thermodynamically stable product, which is water. So we started looking at the literature, actually, and people have been able to do it, but they were not doing it particularly efficiently. So we had the idea, actually, of actually trying to do better. In particular, we had the idea, why not use a platinum-mercury alloy? And what you can do with platinum-mercury is you make an amalgam, so you electrodeposit mercury onto platinum, makes a crystalline alloy at room temperature, and you have isolated platinum sites. And I think what's really important to maintain this oxygen-oxygen bond is not to have two contiguous platinum atoms. So then it meant that you need two contiguous platinum atoms to actually break the oxygen-oxygen bond. So if you have isolated atoms, you can end up making hydrogen peroxide. So we tested it, and this is a current reaction rate as a function of potential. So ideally, you want to be up here. We're very close to ideal. So we're very excited about this result. And we tried to actually think, well, let's commercialize it. And we started talking to people from industry, and they said, no way, we're not working with mercury. So even though I said, well, people are using mercury now, but they said nobody's going to invest in something that's trying to be eradicated. But I think we did actually show that you could actually get really, really high activity. And it was actually quite easy to try. We still managed to commercialize our invention. So we now make hydrogen peroxide in something that looks like this washing machine-sized container, a bit taller. We're now selling units in 15 different countries all around the world. So I'm sure you'd agree that there's nothing more pleasing than to look at the Spanish farmer in Huelva with blueberry farms, making organic blueberries and smiling. But on a more serious note, I think, we're now getting to the point where we've got a lot of renewable electricity, and surplus electricity can drive forward the decentralized production of our most needed chemicals as well. So in my time in Denmark, what I learned a lot. Actually, it was a really positive experience. So it was important to be in the right place at the right time. I really was there. So actually, when I arrived in the department, I was pretty much the only experimental electrochemist. When I left, almost everyone was an electrochemist. But I realized electrochemistry is challenging, but actually really rewarding. So leading a subgroup of 10 talented researchers allowed me to step out beyond oxygen reduction. I'm not showing the results today, but also for things like water electrolysis, CO2 reduction, alkane valorization, and nitrogen reduction. And theoretical chemistry can be extremely accurate in predicting experimental trends. There's volcanoes everywhere. But you need really carefully designed experiments to prove theory. Also, I started to learn about how important it was to speak to context and industry. It was a surprise to me that research actually led to patents of real industrial products like hydrogen peroxide. And another thing I learned is because I pretty much did all my PhD in isolation, the science is actually so much more fun, more powerful in collaboration. So despite all the positive experience I had in Denmark, I also started getting slightly itchy feet. So I remember actually one specific experience. So Yang Xiaohorn from MIT was at the Create campus in Singapore, and she invited me over. Actually, the first time I went there, I realized I couldn't check in. I realized actually I'd forgotten to renew my passport, so everything got delayed by a week. But I went there, so I really enjoyed the food in Singapore, and I really enjoyed the conversations I had with Yang. And I remember there was actually at this restaurant in this photo. She asked me, wouldn't you be interested in rising to the challenge of running your own completely independent research group one day? And to help me in that process, actually, Yang actually helped me get a visiting professorship at MIT in the main campus in Boston, where I taught and conducted research for 6 months. Here's me about to teach. So there, actually, we started continuing with some of the research that I'd been doing already in Denmark on water electrolysis. In particular, in water electrolysis, in the PEM electrolyzer that I showed you cross-section before, the limiting step is actually going from water to oxygen. So this is the reverse of the limiting step in fuel cells. So it turns out, actually, you can make a volcano to describe the catalytic activity for oxygen evolution. This is based on theoretical structures, usually modeled in vacuum. But often, to make these kind of volcanoes, they have to look at idealized surfaces. And it's very difficult to actually calibrate it against experiments and know if it's really the case. And because often they have to make assumptions in the way, and the more assumptions they make, the more onerous the assumptions are, the more difficult to, more they are veering from reality. So the theorists still need us as experimentalists to give them a helping hand. So what was really nice actually there, so in Imperial College, MIT, I started working with Reshma Rao. Actually, I taught Reshma, who's now a lecturer in the department, and we started collaborating. And we actually used surface X-ray diffraction. We could probe on a single crystal, similar to the platinum crystal I showed before. We could actually probe the position of the different ruthenium and oxygen atoms under applied potential. We found previously unidentified intermediates. We even expanded our analysis from multiple surfaces. We found a volcano. So it was quite nice as a proof that we can start to get atomic scale insight into catalyst controlling water electrolysis. So overall, my experience in MIT was also really positive. I thought that I learned on a scientific approach level, we can strive towards the same level of molecular scale understanding on metal oxide catalysts we have on metals. And also in Yang's group, they were also very interested in actually approaches beyond aqueous or water-based electrochemistry, for example, batteries. This also sparked my interest in it. As I also realized from Yang the importance of mentorship to early career researchers. And also, I think what was quite useful in the US is actually people are very aware of the career trajectory. That made me a bit more aware of where I needed to go. So eventually, I thought, okay, I want to go back to I thought about going to the US, but I thought actually I really want to go back to UK, and more specifically to Imperial College. Actually, I applied in 2015 while I was at MIT to the chemistry department. I got an interview, but I didn't get it. I think I was probably too nervous at the time. James can tell you more. He was actually on the panel. But eventually, I did actually come here in 2017. So this is me on the eve of my interview. I remember actually Peter Haynes called me when I was in the tube to Heathrow, and he told me that I got the job. I actually started crying. Actually, a woman asked me, "Are you right, love?" I said, "Yeah, I was crying out of joy." So this is my leaving reception at DTU, the leaving party of my friends in Copenhagen. I'm saying goodbye to my good friends Valeria and Carlotta, and this is my new academic home here. I'm with Luke and Dan, who are in the audience today as well. So this is really nice to be here at Imperial College. It was tough at the beginning because I'd gone from a place where I was extremely well-resourced, having to start everything from scratch again, and then had to teach as well. So I think for teaching, I have had lows and highs. So in particular, at MIT, I had very, very little experience teaching. So and then I had I think students really appreciate it if you can write out equations and explain everything by hand. They don't like it when I do it at all. My handwriting's terrible. And in MIT, they actually complained if you use PowerPoint. So we had to juggle all these different blackboards. It was horrible. I remember actually the first time I taught there, a student told me, "How many more times are you going to be doing this?" I said, we've got another 8 more hours. She said, 8 more hours? That's hell. So it was really, so I learned, and then there's obviously another time, actually, some of you in the audience, I think the third years here, would remember actually, last year when I was teaching my course on corrosion, I went to the gym in the morning, and then I came out of the shower and realized I didn't have my trousers. So I had to teach in gym shorts. But despite that, we are very lucky to have very kind students here. And they did actually, in 2019 to 2020, despite all my faults, I did actually get an award for teaching, which is a positive thing. So I think what's really nice here at Imperial College, there's a lot of focus on collaboration between departments. So even though some of you will be aware, I'm actually based, my lab is based in White City, but I'm here half the time for teaching. We still manage to get along, and there's a lot of multi-departments initiatives. And as Sandrine said earlier, actually, we founded an electrochemistry network at Imperial. So we did a lot. We started in the pandemic in April 2020, and we'd have a lot of seminars, training, and we had industry day. What's really nice is actually because Imperial College has a really long history in electrochemistry. I hope I can visit you. It's a really important area of research. And actually, Today we have about 60 academics, different research groups involved in electrochemistry one way or another, which is actually maybe definitely the largest amount in the UK, maybe the largest amount in Europe. And I think it was quite nice to actually all get together and take ownership of this community. So finally, for my last part of my talk, I know I'm running out of time. I'll try and be brisk. So I'd like to go through some selected research highlights. To misquote Mary, who'll give a vote of thanks, actually, this is difficult because it's like picking between your favorite children. I wouldn't know, I don't have any children, but I'm sorry to those to members of my research group whose research I'm not mentioning. It's just for the purpose of brevity. But so one thing we started being interested in. So I already mentioned ruthenium oxide is the best catalyst for oxygen evolution. We studied that, and we made some really nice research of that with Reshma, MIT, and also in Technical University of Denmark. But it's actually, problem is it tends to corrode away. So actually, as I mentioned earlier in my talk, iridium oxide it's not quite the tip of the volcano, but actually works pretty well. The problem is iridium is one of the scarcest elements on Earth. So we need to minimize this use if we really want to make hydrogen at a large scale. There's a lot of talk now about making hydrogen at scale, but we're not going to do it if we use current technology. So ideally what we'd like to do, often when we try and look for new materials, we just discover new materials by serendipity, and that's the standard way to do it, but we'd like to be more intelligent and do it by design. It would be more fancy. So then we have this volcano, which in principle has a design principle. So I've shown previously the volcano actually translates well for single crystals, but how do it actually translate to realistic catalysts? Can we verify it? Can we refine this volcano? And can we actually move iridium oxide to the peak of volcano so we can minimize the amount of iridium that we use? So actually, so this is a typical example of the iridium oxide catalyst that we use. You can see that this is a microscopy image. You can see they're quite rough. So luckily, I'm partnered up with James Durrant and Reshma Rao and Ben Moss and Cao Liang, a PhD student who's in the audience as well. And in James' group, they've been expert at actually doing spectroscopy. So basically shining a light through the sample and seeing how it changes as a function of applied potential. And so essentially, we got this really nice spectra. I won't go into detail what it means exactly. But what we can tell from these spectra is actually that we can see how strong the binding of oxygen is to the catalyst surface. And as I mentioned previously, that's what we think controls the performance. So actually what we found is that it's not, what really controls the performance is not just how strong it binds it, but how much these different intermediates interact with each other. They tend to repel each other a bit. And we could tell that all from looking at these spectra. So it was really fascinating. And then we actually ended up making a new volcano. And you can see the strong bind side of the volcano ended up becoming a lot flatter than before, which is very, very exciting. So these are brand new results. And so ideally now we're at the point, so we can actually benchmark. So previously it was very difficult to benchmark the actual experiments against theoretical calculation, but now we're at the point where we actually can do that. And working with Lucas Garcia and Aaron Walsh, who are also Lucas as an audience, what we would like to do is to actually feed this information back into the theoretical models and design new catalysts to reach the peak of the volcano. So finally, for the last research example, I'm going to go back to nitrogen fixation to make ammonia. So I already mentioned the Haber-Bosch process, which is used currently to make ammonia. Results in 1 to 2% of global emissions. Like hydrogen peroxide production, because you need such high temperatures and pressures to get it to work, you need centralized production. And then it's often challenging to transport the fertilizers. And you end up wasting a lot of them on the way, and it causes a deleterious effect on the environment. So ideally, we'd be actually taking a business model similar to actually our spin-out company, HPNR, for hydrogen peroxide, but also making ammonia. This is a business model of my collaborators, Nitrovolt. You can actually use electrochemistry to convert nitrogen to ammonia, and then you can actually make fertilizers on site and on demand, and you can stop using excessive amounts of ammonia. And if you got really efficient, you could even use ammonia as a sustainable carbon-free fuel. But to get that to work, you need a right catalyst, and no electrocatalyst works well enough today. Conversely, as already mentioned, nitrogenase enzyme actually can do it under ambient conditions. The thing about nitrogenase is that each catalyst has a huge footprint, and you can pack a lot more active sites onto a metal surface. Each dot here is an individual metal atom, so you can actually get much higher rates if you were to use an organic surface instead. So actually, in my old research group, we looked for years and years and years to try and make ammonia using electrochemistry, and we failed really miserably for many years. But lots of reports in literature start saying they could do it. But we set up a protocol saying, if we were to make ammonia, this is how we proved it. And what we found is actually a lot of the reports in literature, what they're reporting such small amounts of ammonia, what they're actually looking at was actually contamination from the lab environment. So it was actually all nonsense, in fact. So actually we had a paper in Nature 5 years ago. What we found is actually one paper alone actually works as a paper that barely been cited from the 90s in Japan. It essentially electrodeposited lithium, an organic electrolyte, using chemistry very similar to lithium-ion battery. So the challenge in actually doing nitrogen reduction is that you've got competing reaction with hydrogen evolution. So nitrogen, these blue atoms here, very inert, and hydrogen a lot more reactive. And typically, hydrogen will bind to the surface and stop nitrogen at getting there. So I asked my theorist collaborator, is there something special about nitrogenase and lithium that allows it to work? And the answer is simply no. So even like nitrogenase and lithium, they bind nitrogen strongly, but they don't bind hydrogen. They bind hydrogen a lot stronger. So you'll always, if you put lithium or nitrogenase into an aqueous solution, you always get this picture. You get the surface poisoned by hydrogen. So to try and understand how they work, you need to think beyond how we usually think about binding different species, and just to tailor the environment around the active site. So what we found is actually we did some, this is work done by Ollie Westhead. She did a microscopy cross-section using our new cryo microscopy sensor and found actually a very thick layer of a solid between the electrolyte and the actual electrode. This is a battery scientists know this is a solid electrolyte interface. So what we think is happening is actually this interface allows nitrogen to go through and moderates access to protons and lithium, so that's how we can actually make ammonia. So it turns out that this is work done by Matthew Spry and Ollie Westhead. So it turns out that actually ammonia's nitrogen production using electrochemistry is really sensitive. Just changing a salt to water concentration, you can change the Faradaic efficiency, how much charge is going towards ammonia enormously. And we're trying to find out why this is the case. But the good thing is there's been a lot of progress in the field. Now it's surpassed my own expectations. Now the actual efficiency, how much current is actually going to ammonia, is approaching 100%, but there's still a big bottleneck. So the potential needs, so the push required to get the reaction to work is enormous. And that's because you need to electrodeposit lithium. So lithium wants to be a salt. It doesn't want to be in the metallic state. And this sets a huge bottleneck on the reaction, especially if you want to use ammonia as a fuel. So I again turned to my theorist collaborator, Alexander, and also to Roman Todt, who's in the audience. We thought, what other alternatives could there be? So here's actually the reactivity towards nitrogen as a function of the reduction potential, how easy it is to make a metal out of these salts. And lithium is actually the most extreme here, and that's why it's good as a battery. But it turns out a lot of other materials like calcium or magnesium, even chromium, molybdenum, tungsten, in principle could work a lot better, and they're very reactive towards nitrogen. So we thought, okay, let's try some of these. Actually, they didn't work, the ones we tried, but just the same week as we published this data, so my now arch rivals, my former research group in Denmark, they actually found that actually calcium, which we were predicted to work, actually did work. But they used the salt. It was admittedly a little bit more difficult to synthesize than the ones that we actually used. But I still think, so what I like to say about nitrogen reduction in general, it's very, very sensitive to the exact experimental conditions. It needs a lot of optimization. I have a lot of hope that we could actually carry out a lot more efficiently than now you can do with lithium. You just need to optimize it correctly. So now I'd like to bring me to the end of my talk. So at Imperial, I've learned importance of support to friends and family outside work. I have a lot, and I'm very happy a lot of you are here today. So tenacity is key. So you need to try again. So when I came here, I had no funding for the first 3 years, so that I eventually got a fair amount. So I think there's much to be gained by getting out of your scientific comfort zone and translating knowledge to and from adjacent fields. So Magda's got me into biomass valorization. There's a lot of and even I've got a little bit into battery science. I didn't have time to talk about it today. The thrill of teaching intelligent students, the joy of leading a group of brilliant researchers who are now thriving in their careers. So they've got lots of prizes, permanent positions in industry and academia. So I think it's important. What's really nice, Imperial can break down the borders between departments. You can interact with people from other departments very easily, much more than previous institutions where I worked, and get out of your silo. I think it's really, really important to find the right colleagues to build a trusting network. And also it's really important to try and find out how you can make your research useful. So for example, I think what's quite nice here, we've got a lot of systems engineers, and they can evaluate what's the availability of different nascent technologies. I was going to go through different technologically important challenges in electrocatalysis. I think we're running out of time, so I'll skip over this. But I think what was quite interesting actually means to actually get to the future is now we've all heard about AI and machine learning. I think in parallel, actually, there's a lot of advances in robotics. So we can actually get robots to do our experiments. I'm working with a few of you here, in particular at Magda. We're trying to do that now to maximize reproducibility and throughput so we can actually put data into machine learning models. And finally, so I've talked about kind of scientific issues and what's really important. But actually what's really, what I know from my research group, there's so many in my research group actually getting jobs easily, and I think they're really talented and they deserve these jobs. But I think there's a lot of demand right now for people working in electrochemistry, but we're really lacking enough people. So we need, just the same way as I feel it's a nice place to work in our departments because I feel it's actually normal and comfortable to be a gay man. I think we need to make other people from other underrepresented groups feel the same. So we need more people. We need to do more outreach. I've done a little bit, but there's other colleagues like Jess Wade in the department who do a lot more. I think this is really, really important if we want to really move forward in our field. So finally, I'd like to thank commercial sponsors and funding bodies. And I'm being a bit controversial. I have I'd like to thank my former research group in Denmark. One of the members is here today because he's also in my research group now as well, Anna. And then also, I'm going to be a bit controversial. I'm not going to thank all the other internal collaborators and external collaborators. Far too many to mention. I'm scared I'm going to miss someone out. I'd like to finally thank my research group. They've been very, very patient with me over the years. So we started with almost no resources, no money, no lab, and we moved lab multiple times even during the pandemic, and they built an amazing lab here in White City, you can see in the video. So this is them right back in 2018. I just had 4 PhD students and a couple of master students. They fitted into my living room. And then this is us last year. We're a much bigger group now. And then this is a joint group dinner with Magda's group. We had, how many, 80, 90 people? And a third of whom were from my group, actually. So it's really grown enormously. So I've talked very specifically about certain reactions, looking at a lot of different reactions. Finally, I know I'm running out of time. I'd like to thank you, the audience, for your patience, for listening to me today. I'm looking forward to talking to you at the break. I'd be delighted to answer maybe just 2 quick questions, right? Maybe we've run out of time.
Hello? We on? Hello, right. So it's customary in these occasions to not take questions. But of course, Ifan is being not conventional, so he's very happy to take just a couple of questions, preferably not from the in-house electrochemists. Has anybody got a question? No. See, that was why he's such an amazing teacher, because it was all crystal clear. There are no questions. So, well, thank you, Ifan. I think you just said I used to be cool at the beginning of that.
No, I didn't say it. I said you still.
Yeah. So it's my great privilege to give the vote of thanks to this. And I guess that since I'm now not the cool person, and one of my jobs is to give you the old, interesting, slightly nerdy fact about Imperial College. And in 1908, most of you probably don't know, in White City, where Ifan's lab is, was the place where London hosted the first of its Olympics. And it hosted the Olympics in White City in 1908 because it had to be moved from Italy because there was a volcanic eruption, Mount Vesuvius. And it's taken almost 100 years for a more interesting story about volcanoes and White City to emerge here in the form of Ifan. Now, you all know Ifan. You're all here. You all know what an amazing person he is. I think I've been at Imperial College 25 plus years now. I've seen many academics, new colleagues come and go, and many brilliant academics and brilliant students. But it's very rare for somebody to come into an organization like Imperial and catalyze such dramatic change that Ifan has done. He's the human embodiment of an optimum catalyst. Just by his sheer enthusiasm, energy, generosity of spirit, eagerness to collaborate across all boundaries. There are no boundaries of departments, no boundaries of faculties in the way Ifan approaches his work. And it's an absolute joy to engage with him on science and beyond science. I think those of you that have seen his trajectory would know. And we do warn our students not to go north to do their PhDs, just to be clear. Much safer to stay here. Oh, he's been through, quite challenging times in his career. But you can imagine him having a level of resistance that kind of belies his gentle exterior, because he really cares about what he does. And he puts that passion, that enthusiasm, that carefulness into his work. And he has a purpose. If you go back and look, again, I'm going to be nerdy here. If you go back to look at Imperial's founding charter in 1907, it's written into our legal framework, passed by the Houses of Parliament, that our founding mission is to be useful. And I think seeing Ifan wrap his excellence in science, his deep understanding of knowledge, his really transdisciplinary approach to science, and then at the end, encapsulate what we are here about, delivering impact from doing brilliant work, working with brilliant people, and being useful. Right, I'm not going to say too much more because he's clearly going. Stop it, Mary. It's a great privilege to be your collaborator and your friend. We're very happy that you're Imperial. Your rise to professor was, dramatic, but maybe too long, right? So because he came in already a fully formed, brilliant academic. I'm now standing between all of you and the conversations with Ifan and the celebratory drinks we're going to have afterwards. Please join me in one more round of applause for this amazing lecture. Brilliant science.
Thank you.